main topic left to cover in this unit is calculus. So I'll be going through the theory of the derivative with you, and Saeed, kind of in parallel, will be going through the theory of the integral with you. And of course, there's strong connections between those two, which I'll talk a little bit about as well. And then there's also a topic on group theory, a short introduction to group theory, which will form the last part of my material in the unit. But because that calculus material on differentiation and integrations is all about the study of functions defined in real numbers, it's worth having a separate little chapter here just to introduce kind of standard terminology and definitions relating to functions. Okay? I'll do a bit of work with the pen and paper this morning as well. To support what's in the notes. And now, a lot of this will be familiar to you in various guises, because of course, you know, in your mathematics to date, you've been using functions all over the place. So it's not as if this is a new topic, so to speak. But we do want to set up some good formal definitions and some nice terminology as well for how to talk in a rigorous way about functions. Okay? So first of all, our definition of what a function is given in 3.1. So a function f, and part of the definition of a function is talking about these two sets. So it goes from a set x to a set y, and it's a rule, definitely clear rule for assigning elements from the set y to elements in the set x. Okay? But it does it in such a way that for any element from the first set x, there's only one element from the second set y that's associated. So our functions are so-called single-valued functions. Okay. So it takes you from elements of x to elements of y. And you can see the terminology and notation there in definition 3.2. The sets x and y have special names. We can refer to x as the domain of the function, and we're going to use the phrase codomain, the term codomain, to refer to y. Okay. And elements of the domain x can be called arguments of the function. So the arguments are the things that you apply the function to, and then the elements of the set y are called values of the function, potential values of the function. Okay. Or more correctly, the elements f of x, f applied to an argument from the set x, that gives you a value of the function which lives in the set y. Now, at the moment, there's no requirement that every element of the set y occurs as a value of the function. Okay? So the set y is just the location where all the values of the function live, but we're not having a requirement that all of the elements in y actually occur as values. Okay? So there could be some elements knocking around in that set y which aren't equal to f of little x for any little x. Okay? I will attach terminology to that kind of situation shortly. But we do have a requirement that the function f, it has to be defined on every element from the domain. Okay? So we must have, in principle, an associated element from y to every argument x from the domain. So the function f can't be left undefined on any elements from the domain. Okay? Now, in this unit, and in fairness, a lot of the time in maths, certainly in applied maths, the functions we're talking about are real valued functions. Functions going from the real numbers or some subset of the real numbers to the real numbers. Okay? So, I mean, let's look at a few familiar examples quickly. You've got the square root function, S, say. So these are just examples plucked from the large collection of functions that you're familiar with. So you could set up the square root operation as a function S from R plus to R. So R plus would indicate the positive real numbers. Okay? Positive real numbers. So the positive real numbers is the domain, and the real numbers, we can take the real numbers as being the codomain. And the rule that associates, the rule for the function is simply to take the square root of the argument. So S of the argument X is simply the square root of the argument. And you can see here that not all elements of the codomain occur as values of this square root function X. Okay? Because all the negative real numbers, they never occur. No, sorry, stop that. I was speaking wrong. As I've set it up here, because I've set R plus as just the positive real numbers, that means you'll never, the element 0 in the codomain will never occur as a square root. Okay? So if I'm talking about the positive real numbers, that's everything strictly bigger than 0. So because I have excluded 0 from the domain, it means that 0 will never occur as a value. And yeah, if we're taking the positive square root here, which we should, yeah, so we'll understand this square root procedure to be giving us the positive square root. And yeah, then any negative real number will not occur as a value of this function. Okay. Then you've also got, like, just to take one of them, the sine function. You've got these important trigonometric sine functions from ratios of sides and triangles. And you could set that up as a function from the real numbers to, and you could choose a fairly well, precisely defined codomain of the interval from -1 to 1. So that square brackets -1 to 1 is denoting the interval of real numbers from -1 to 1, including the endpoints -1 and 1. Okay. So those are just some examples taken from the large collection of functions that you know about, just to talk about some example domains and codomains. We can also talk about the range or the image. So the range or the image is a subset of the codomain. And it consists of, so you can use either term to refer to it, the range or the image of the function. It's the set of all the values of the function. That may be all of the codomain, but it might omit some elements from the codomain. Okay? So the image of G is just, so here we've set up G as a function from the domain V to the codomain W. So the image of G will just be the set of all the values G applied to little v, where the element little v ranges over all the elements of the domain V. Okay? Now we won't, it can become a bit laborious all the time to specify carefully the domains and codomains of the functions that we talk about. Often we will talk about functions without explicitly referring to what their domains and codomains should be. I mean, most of the time it will be clear from the context what it should be. And any time where it does very much matter exactly which codomain we're using, or which domain we're using, you know, we should explicitly state that, okay? But we should remember that, you know, it's part and parcel of the formal definition of a function is a specification of what the domain is and what the codomain is. There's a few more definitions to look through. I want to show you some stuff on the screen as well. And that there are, first of all, to talk about one visual way of thinking of functions. We're going to see a second way, We're going to see a second way shortly, which is more suitable for other situations. So this way is a, well, I don't think there's any standard name for it, but I'll call it a Venn diagram picture. Venn diagrams are normally used, I mean, you've seen those in set theory with Said there, and they normally show overlapping sets. You can have a collection of sets, and the Venn diagram shows all possible intersections amongst those sets, of the intersections of different orders between the different sets. But there's a kind of a similar type of picture which we can draw for functions. Okay, and that is simply to think of. So it's nothing particularly standard or anything, but just to think of the domain X, say on the left of the page, and the codomain Y on the right of the page, and the function f. Here we think of the function f as some kind of process, or some kind of assignment, which is taking elements from the domain across to elements in the codomain. And we can show these assignments with the use of arrows. Okay? So this x here and this y here, we've got y equals f of x for those two particular elements. This element y, little y in the codomain y, and little x in the domain x. Drawing the arrow between them indicates that y is the value of the function f evaluated at the argument x. Okay? Now, I'm sure you may well have seen that kind of picture drawn. Okay? So all the other, so part of being a function means really to fully complete this kind of picture, I must draw an arrow across for every element in the domain. Okay, so that looks like a well-defined function. Okay? That arrow is going from every element in the domain. I don't worry too much about exactly replicating my arrows. That's not important. But you'll notice a couple of features of this which show parts of the definition of a function. Each element in the domain has one and only one arrow coming out of it. Okay? So the function must be defined on every element in the domain, and the function only assigns one element, one value to any given argument. Okay? So we don't have two arrows emanating out of any of these elements in the domain. Nor do any of the arrows suddenly branch into two arrowheads as they go across into the codomain. And also illustrated here are some aspects of how a typical function might behave. There are some unused elements in the codomain. Okay? But that's not a mistake or anything. That's not a misrepresentation or anything. So there are some elements here in the codomain that do not occur as values. Okay? These ones here. So that can happen. Like our square root function, which went across to the real numbers, but if we're taking just a single positive square root of any argument, then none of the negative numbers would occur as values. And also, for some elements in the codomain, you've got more than one arrow arriving. That's okay as well. Okay? Some elements of the codomain can be the value for two or many more different values in different arguments in the domain. Okay? So that's allowed. That's not breaking our definition of a function. So here you see a value for more than one argument. And that's okay. Certainly a valid looking function. And you could even have 2 or 3 or 4, any number of arrows coming into that value that you want. That would still be a function. But as soon as you draw 2 different arrows coming out of an element in the domain, coming to 2 different values over here, then that is no longer a function. It still might be a valid mathematical object to look at. Mappings where you assign more than one value to a given argument, there's nothing unmathematical about it, but it shouldn't be called a function in the way that we've introduced the term. Okay? Some people call them multi-valued functions, or many-valued functions. Okay. Now this kind of way of conceiving of a function is particularly suitable to the next two definitions we're going to introduce. So the first one is injectivity, or more informally known as the one-to-one property. Injectivity. Now this is a property that a function may have. A function might have this property. Not being injective, so I'm defining it by defining its negative. So a function fails to be injective is when a value y is the value for more than one argument. So it's exactly this situation where you've got a value here in the codomain which is the value for two or more different arguments. Okay, here I've drawn one where it's 3. But as long as there's some element in the codomain which is the value for more than one argument, then the function fails to be injective. So that's non-injective behavior, non-one-to-one, because this is kind of 3-to-1 behavior in this example. Right? So 1-to-1 is where you only have, for any particular element in the domain, you have at most one argument that gets sent to that. There may be no argument at all that gets sent to that y in the codomain, but if there is, there can only be at most one. So another way that it's typically represented, and this is more logically, so, well, it's written there in the notes, but for this x and y here, and this would say that if for every pair of elements in the codomain, if f, for every pair of elements in the domain, for every x1 and x2 in the domain, if it's the case that f of x1 is equal to f of x2, that must imply that really that x1 and x2, they aren't two different elements. It's just the same element being talked about twice. The same element being named by two different variables. So this is how it's defined in a positive way. So f is injective if and only if, so this is the other way of defining it, to define it in a positive way. So you should, when you're studying this, you should certainly kind of meditate on this a bit and appreciate that these two ways of defining it are defining the same thing. Okay. You can say a function fails to be injective when there's an element in the codomain which is the value for more than one argument. That's defining it in a negative way. To define it in a positive way, you say f is injective if and only if this implication holds for every pair of elements in the domain. If f of x1 is the same as f of x2, that can only happen in the kind of trivial case where x1 and x2 are actually the same element. You just named the same element using two different labels. So you just label the element in two different ways. So that's injectivity. And this Venn diagram picture of the function is particularly suited to show, well, certainly showing non-injectivity. So you can use either term to either the word injective or the word one-to-one. One-to-one is kind of more descriptive. It actually, we can deduce from the name, it gives certainly a strong clue to the definition. Injective is the more technical sounding term, more impressive. People are generally more impressed if you use the word injective. Now, hand in hand with that, a similar kind of property, except this time focusing more on the codomain, is surjectivity. Or this is more colloquially called the onto property. Now again, it's defined in the notes. On the page here, I'll stick with my x, y, and f. It's defined in the notes, talking about a g going from u to v. So here's a function f, some kind of mapping from the elements of x to the elements of y. And here the picture is that, okay, so I'll assume in this picture that all elements of y are shown. So I have some bunch of dots over here, it could be an infinite number. These are the elements of y. I'll assume that they're all there. And then the function is surjective if every element in the codomain actually occurs as a value. I won't bother showing where these arrows are coming from. That's not important. They're all coming from the set X, obviously. I'm not interested in showing or being able to talk about the elements where the arrows are coming from, just that they are coming from elements in the domain. So a function is surjective when every element in the codomain occurs as a value. So the kind of logical kind of predicate way, or kind of logical way we can define that is saying that f is surjective if and only if, at this time it's the logical statement is ranged over elements in the codomain. Before it was, the scope of the statement was over elements in the domain. Now we're saying for every element in the codomain, you've seen the backwards e with psi e? It exists, yeah. So for every element in the codomain, there exists an element x in the domain x such that, well, you don't really need the such that if you're talking formally, logically. So what we want here is f of x equals 1. So it says, no matter what element in the codomain you focus on, there is always at least one element in the domain such that the function maps that x to this y. But this is surjective behavior. So this is describing what's going on in the picture. If we take it that all the elements of y are shown, every element in y has an arrow coming in. And I purposely indicated a range of behavior there, so some of the elements only have one arrow coming in. They're just the value for a single argument. Other ones have more than one arrow. So that's surjective behavior. Now, it's important to note, and this is a slip-up that I see people making every year. These are two independent properties. They kind of go hand in hand. It's important to consider them together. They often crop up together. But it's important to note that they're two different independent properties. So all of the four combinations, we can construct functions showing all four different types of behavior. Obviously, any one function can only show one type of behavior, but all four different combinations of injectivity or non-injectivity and surjectivity or non-surjectivity. So there's four, when you've got two properties that can be true or false, there's four combinations of them in total. It can be injective and surjective, injective and non-surjective, non-injective and surjective, or non-injective and non-surjective. And that's what I mean to say that they're independent. Being injective doesn't mean you're not surjective, or it doesn't mean you're surjective either. And being surjective, well, you can still be injective and you can still be non-injective. Okay? So they're independent properties. But every year I see people kind of getting mixed up and saying, well, this function is injective, therefore it's not surjective. But there's no therefore link between them in general. Right? And if you look in your notes, example 3.2. So example 3.2 talks about the sine function. It talks about the sine procedure or sine process in two slightly different ways. So the first way is to think about the sine function, but only going from the interval 0 to pi over 2 to the interval 0, 1. So these are open intervals, so they don't include their endpoints. We got 0, we got maybe pi over 4, should show that as well, and pi over 2. So the function sine is 0 at 0, and why am I showing pi over 4? So the sine function there kind of goes like this: 1, 0. So this is injective and surjective. Every element in the codomain occurs as a value of the function, meaning every number between 0 and 1 on the y-axis every number between 0 and 1 is the sine of some angle between 0 and pi over 2. Okay? That's why it's surjective. And it's injective because there isn't any case of two different angles having the same sine value. And what we're showing here also emphasizes the fact that, really part and parcel of the complete definition of a function is the specification of the domain and range, the domain and codomain. Because if we talk about, the same process, the same procedure, taking the sine of an angle, but this time set the function up as going from this domain, now the open interval between 0 and pi, and this codomain, the open interval between 0 and 2, then suddenly the properties of the function change. Now, the sine function very roughly looks like this. Now this is not injective, nor is it surjective. It's neither. It's not injective because of examples like this. So here's two different angles. But you see they both take the same value under the sine, under this sine function. Two different angles there having the same sine value. And there's also plenty of elements in the codomain. See, the codomain is now down from 0 to 2. There's plenty of elements up here, which are not the value, which are not the sine value of any argument. Okay? Sine just remains on this domain. Sine just varies between 0 and 1. It doesn't go any higher. So there are certainly elements here which do not occur as values of the sine function. Anything strictly greater than 1. Okay? So the same underlying process, taking the sign, even taking the same underlying process, you can set it up as different functions. They're different because they've got different domains and codomains. Different functions showing different combinations of injective and surjective behavior. And you can certainly you can realize the other two combinations, injective and not surjective, not injective and surjective. By adjusting the domains and codomains, you can still use sign to produce the other two combinations. So exercise, define different sign functions by adjusting the domain, by adjusting the domain and or the codomain in order to show the other two types of behavior. To illustrate the other two combinations. Okay, so you should have to think about that. Okay, any questions about those properties that you'd like to ask? Anything you'd like me to clarify on them for you? Yes.
You know how a value in the domain can't have two different codomains?
Yeah. So
values.
Yeah. But when you're speaking of the things in the domain, you should call them arguments. Because then you can say arguments in the domain and values in the codomain.
Would that not then make the square root function not a function?
Well, yeah, but I said it a few times, so maybe it should be part of the definition that we're just taking the positive square root each time. So yeah, so we need to restrict it. Yeah. No, but you're right. That square root process really, under the full meaning of it, would be a multi-value function.
Yeah.
Yeah, because a number can have, well, it always has two square roots. If you look at cube roots or fourth roots, you can have, and if you look at it in the complex numbers, they can have even more. So yeah, you're right.
Okay.
It's maybe not the best example to illustrate function behavior because yeah, it's kind of wanting to be double value. Yeah, no, that's good. And there's kind of a feeling that the best kind of behavior is being both, being injective and surjective. So there's a special term given to that in definition 3.6. That's bijective. So a function that is one-to-one and onto is termed bijective. So these are functions which use up all the elements in the codomain, where everything in the codomain occurs as a value, and they're functions that only display one-to-one behavior. They never display 2-to-1, or worse, 3-to-1, 4-to-1. They only ever display one-to-one behavior. The bijective functions are kind of considered to be the most well-behaved functions, and there's a strong meaning for that, or a strong consequence of that, which we'll see shortly. The bijective functions are the functions which have inverses. Okay. Now, in the rest of page 25 there, you'll see there's a number of definitions, and this just, I mean, I think you're all familiar with these anyway. You've certainly added functions together and multiplied functions together many times in your careers. So this just records the definitions. That we can have an algebra of functions themselves. So this is where you're using, say, real valued functions taking values in the real codomain of real numbers. Well, if you've got that set up, then you can add together functions. So you see in definition 3.7, you can add together functions f and g, and that produces a new function. A new function which, when you apply it to an argument x, it gives you the value f of x plus g of x. Similarly, with multiplying by, you could call them scalars, or multiplying by coefficients lambda, you can multiply a function by any real number. Gives you a new function whose value, when evaluated at an argument x, is simply lambda times the value of the old function f. In the same way, you can multiply together functions and take reciprocals. Well, you can take reciprocals as long as you never encounter a value of 0 for the function f. What's important to recognize here that these operations here on the right-hand side here, these operations on the right-hand sides of these definitions, those are the familiar operations between numbers. And using those, then, we get these new operations, if you like, which are not operations between numbers, but the things on the left-hand side are operations between functions. So that's one thing you want to take away from this chapter as well, that we like to regard, in certain situations, which come up a lot, we like to regard the functions as objects in themselves. Okay? They aren't just something that happens between numbers. We like to regard them as kind of fully fleshed out objects in themselves. So you can take two functions and add them together, and it gives you a new function. You can take two functions and multiply them together, it gives you a new function. Now, over the page then, it introduces the important operation of composition. Now, composition is when you run two functions together. But before we look at the definition of that, let's look. I told you I was going to give you two kind of visual ways to think about functions. So another useful way to visualize functions is as, what could you call it? I mean, there's various things for these. People talk about it could be like a black box picture for a function. So a black box idea is the idea of having just some machine contained in a black box, and you feed it inputs and it gives you outputs. And maybe the inner workings of the box are hidden from you in some way, or something I don't think there's really any kind of standard term for it. So it's just a box machine, let's say. So don't worry too much about what it's called, because really the idea is to just think of it. Really the idea is the visual picture of it. It's just a box, some kind of machine, and it takes inputs. The kind of normal, typical way to visualize it is inputs come in from the left, the inputs go into the machine, and the values come out. So the arguments go into the machine, arguments x go in, and values f of x pop out to the machine. And inside the machine, it performs the function on x. Now this is a particularly nice way to think about functions when you're talking about the operations of composition. Composition is the operation of running two functions together to make a new function. So I'll follow exactly the setup here. So we've got f and g. We're going to f goes x to y and y to z. So we've got sets x, y, and z, and f goes x to y. So we've got one box here, f, which takes arguments from x and gives you values in y, and then we've got another function g, which takes arguments from y and gives you values in z. The two different functions here, both illustrated or conceived of as these machines inside boxes. And you stick a little x in here, and out comes an f of x. But you see, the f of x that pops out here, because it's living in the set y, it can be an argument to the box g. So there's no reason why we can't feed f of x into g, because f of x is an element in the domain of g. Well, if you do feed f of x into the box g, what comes out, of course, is g of f of x. So whatever you feed into the box g, out comes g applied to that input. So joining these two boxes together, or you can even think of it as joining the output from F to the input to G, this gives you a new box called G after F. G after F now is a function from the domain of X to the codomain of G. Skips past Y or travels through Y. We've got a new function which takes inputs or arguments from X and it gives you values in the set Z. This is referred to as composing the two functions. And there's an example shown in 3.3. Now in example 3.3, I take two real valued functions, f of x and g of x. They're two polynomials. F of x is x squared minus 3, g of x is 2x plus 3. And you can see in the notes there how we worked out formulas for f after g and g after f. But they both give you quadratics. You can see in the example there in the middle of page 26. But it's important that they give you different quadratics. Okay? F after g gives you 4x squared plus 12x plus 6. G after f gives you 2x squared minus 3. And of course they're different. So an important point here is that composition, even when you can do it in the two different orders, that to be able to compose functions in two different ways, you need them to be going from the same. The domain and codomain needs to be the same set for each function. So if you have a g going from x to x and an f going from x to x, g after f and f after g are typically different. They don't have to be the same. Indeed, it's unusual when they are the same. Okay? So compositions, the technical term here is that composition is not commutative. Composition is not commutative. A commutative operation, commutative would be a situation when A star B equals B star A. Now, I'm not saying what the star is, but star is just some operation between elements. Here we're talking about composition between functions. We use the little circle to denote the operation, but an operation star is commutative when A star B is equal to B star A always. Now this example 3.3 shows you that function composition does not have to be commutative. There's an example of two functions which when you compose them in the two different ways give you different answers. But it's not, and we'll finish with this nice example. It's a kind of a silly example in a way, but it gets the point across. It's extremely special behavior when two functions are commutative with respect to composition. Okay? If you ever get functions that when g after f is the same as f after g, that's kind of very extremely special behavior. And it's not really a mathematical fact, it's more a fact just about reality. That because what we're doing when we're composing is we're doing two operations. And typically when you combine two operations in sequence, it generally makes a difference the order in which you do them. The example I like to use, it's a bit silly, but let's say there's two operations involved in making a cake. The first operation is you mix the ingredients. You get your flour, your butter, your water. You watch Bake Off, you'll know. I don't watch Bake Off, so it's at least flour and butter and milk, say. Maybe something else. But you mix all the ingredients in the bowl. You get a nice mixture. That's the first operation. The second operation is you bake it. Right? You put the mixture into the oven, and at the end of the baking procedure, out comes lovely cake. So those are the two operations, mixing the ingredients and baking. If you do those in the opposite order, you first just get your separate ingredients. A pile of flour, block of butter, a glass of milk. You bake all the ingredients first. You do the baking bit first. The butter melts, the flour kind of sits there and burns, the milk evaporates a little bit. And then you take them out of the oven and mix them. You don't get a cake. The result is very different. You just get a mess, right? A non-appealing mess. So it certainly makes a difference, the order in which you combine operations. And when you start to think about it, that's true basically of everything. Any procedure you do which involves a sequence of steps, if you change the order in which you do the steps, either the thing will fail, the procedure will just break down in the middle, or if it does complete, if it is a valid way to carry things out, the result is usually completely different to the result from the other one. Okay? So I think there's, in the tutorials at least, there's examples 3.4 you could be working on. Not too many things opened up for us. We've mostly been talking about terminology and so on. So we'll finish this chapter off. Next week. Week 8. We'll finish it off week 9.